Okay, well, I'm going to talk about what's special about hypersonic flight, what's different to hypersonic flight than flight at any other flight regime, and where do you do hypersonic flight? Why would you? Why would you travel so fast in the atmosphere where you get very hot and there's lots of friction around? Well, hypersonic flight, by implication, you have to be in an atmosphere. Out in space, you go very fast, but you don't really call it hypersonic flight unless you're in an atmosphere. And going very fast, there are a lot of aerodynamic effects like lift, drag, heat transfer. They can be useful to you and they can be a disadvantage. We'll look first about where do you fly and what sort of things do you do when you're flying. Depending on what your mission is, that has a strong influence on the shape and the design of the flight vehicle you use. We can categorize certain commonly used flight paths. The most well-known is the Reentry Corridor, when you come back from outer space and it's a good idea to stop before you hit the ground because you're traveling very fast. The cruise corridor, that's when you want to travel at a constant speed and just travel places fast. The cruise corridor actually hardly exists at the moment because we don't know how to do it in a sustained manner. An acceleration corridor relates to when you're trying to accelerate to go through the hypersonic flight regime and get into space. Again, it's not something we do particularly at the moment because we don't have the propulsion systems to facilitate it. And then there's more likely, the common things is suborbital space hops, where you want to shoot something up very fast, get out of the atmosphere, and then come back in again at some distant location and travel very fast as you do it. What you might think of a hypersonic flight trajectory actually isn't. The normal way of getting into space is not to fly hypersonically. You need to go at speeds in space that are much faster than hypersonic, but actually you try and do that acceleration outside the atmosphere. So the space shuttle, for instance, although it'll have a nominal Mach number of 25 when it's in space, very hypersonic, it leaves the atmosphere by about Mach 3. It goes straight up and out of the atmosphere as quickly as it can, because it's not a good place to be when you're traveling very fast in an atmosphere. Lots of drag, lots of heat transfer, you're likely to burn up and self-destruct. Well, we've been using reentry corridors for about 60 years, since the first missiles went up into space. The main function of a reentry corridor is just to lose speed. And in doing that, if you want to survive, you've got to control your drag, your deceleration. You can easily be destroyed just through too many g-forces, and also the heat transfer. Lots of energy around which can burn you up if you're not careful. There are several categories of ballistic trajectory. The ones we're going to look at here are the so-called ballistic trajectories, where we have only drag and no lift. Most flight trajectories will actually make use of lift to a certain amount, like the Apollo coming in had a lifting trajectory. But ballistic trajectories are very good because you can get analytical solutions for them, and we often use a ballistic trajectory as a starting point for a design study because you can get quite close to what a flight path might really be, and you can get analytical solutions, which is a good thing to have at the start of a design process. You know roughly where you're flying, which is how high, and I guess which atmosphere you're in, and how fast you're going. And then you can have a stab at designing a vehicle. So ballistic entry relates to using drag forces to slow yourself down. There are three basic categories within a ballistic trajectory. Air capture has not actually been done yet, but we talk about it a lot. And that relates to coming in from outside of Earth on a so-called hyperbolic trajectory, outside of gravity's influence, and you have to slow down enough in the atmosphere to get captured, but not actually to land. Aerobraking can be used to adjust a capture orbit by ducking down into the atmosphere for a little while and losing some velocity and then going out again. You might wonder, why would you do that? Well, if you want to change your orbit and you don't use braking, you have to fire up rockets, and rockets are heavy and they have to carry fuel. So it's a way of losing your speed without having a propulsion system to do it. And the most commonly used trajectory course is total reentry, where you come in from outside and you stop and you adjust things to get the right control of velocity along the way through the atmosphere. Okay, well, what sort of vehicle would we like to build for re-entry? You know, traditional aerodynamicists like to make things that look nice and sleek and sort of sexy, and it turned out, you know, they don't work very well for re-entry purposes, because the purpose isn't to generate lift and to fly long distances with minimum amount of fuel, it's to stop. So typically re-entry vehicles are characterized by surfaces aligned normally to the flow, so the force that acts on them is pushing against your direction of motion. So in any field of engineering, a good idea as a starting point when you go into a new application is to look at what people did before and see if it's going to work. If you don't do that, you're likely to reinvent the wheel. So when we first had the capability to go hypersonically in the 50s, we looked at what's a traditional aerodynamic shape, and it's like you see on the left there. It's something long and slender looking. And they analysed that, they tested in wind tunnels, and it really didn't work very well. You can imagine if you use that long, skinny thing as a brake, the main surfaces you have for braking are friction surfaces. It's like trying to slide down a rope. You rub all the skin off your hands through friction, and that's not the way to go. So big breakthrough came in the 50s when they decided you don't make long, slender things, you make blunt bodies, and that's been the way we've done it ever since. And it's sort of self-evident what you do. It's blunt, it pushes the air out of the way, slows you down, and the heat transfer is minimized. Even if you look at something that's quite streamlined, like the space shuttle, on re-entry it flies more like a brick. It comes in at like 40 degrees to the flight path, and most of the surfaces are pointing forwards. Obviously it generates some lift as well, which we're not going to analyse in this course, but it's a blunt body dissipating heat. You see the same vehicle later when it comes into land, it flies in a very different mode. Here is an example of a flight vehicle coming through the atmosphere. All the energy is being dissipated. There's radiation in the shock layer, you can see it glowing, and when it lands and people come out, hopefully they survived, you can see it's a very simple blunt body shape. It doesn't really look sophisticated, but actually technically it's a very advanced design. Getting people back from space alive and safe is not easy. This is a classic design called the sphere cone configuration, shown here in a Titan entry capsule. You want to make the thing as blunt as you can because that's the most efficient shape. Of course, if you make it blunt, you introduce another problem. All your drag forces are on the front because your mass has to be behind the front surface, so it's effectively unstable, as if you try and balance something with all its weight beyond the point of support. You see those front surfaces are flared back a bit, and by flaring them back, you reduce their efficiency as an aerobrake a little bit, but you're moving the centre of drag further downstream, so it's easier to handle the stability. So that's the classic shape we use for re-entry into the Earth or other planets at high speeds as well.